All right. Now today we have started the course, and we saw how to. We talked about how this course will go on. Now we can start the lecture, the first lecture, which must start with the definition of information. In that sense, this thing is, or this course of signal compression is somehow related to information theory, because we do compression of the source according to how much information it contains. Okay, if it may be a large data, but it does not contain a lot of information. Of course, by information, right now we are talking about mutual information, standalone information, but it could be conditional information as well. The conditions are that the receiver side already knows some background. So the amount of residual information that the content carries may be even smaller. So, but nevertheless, we will try to reduce the number of data that is stored or transmitted, reduce it to as low as its pure information. Otherwise, the data may be large. For example, it may be a complete blank image like this, totally blank, right? And how much information does it contain? It is, let's say, 1000 by 1000, and let's say grayscale, so times 1 or 8 bits. So I can see that it is 8 million bytes or 8 megabytes originally, the file, for each pixel, which is, let's say, white or black, whatever. It's just a constant blank color. But the information that it contains is very marginal. First of all, I don't know that it is blank. So it is blank is something that that's the amount of information that I have, a blank picture. But it was 8 megabytes. Now, instead of that, if I can find a method to say that it's a blank picture, sorry, blank picture. If I can find a method to convert from the left-hand side 8 megabytes of image data, picture data, to the right-hand side, which is saying just blank picture. And by the way, it's saying blank picture. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's only 13 bytes. So 8 megabytes to 13 bytes is the compression ratio that we make. It may be even less than these 13 bytes, depending on the amount of possibilities in the information at the right-hand side. But even this one is a huge compression. And if you try to compress this 8 megabytes, oh, it's not it's 8 megabits, excuse me. Let's not make a mistake here. It's 8 megabits. So essentially it's 1 megabyte. This kind of a compression is huge, and it's uncomparable to, let's say, JPEG compression of this image, or if you compress using zip or anything, whatever that you may have, it will still be way more than 13 bytes. But now I made it 13 bytes. But there are a lot of problems about doing this. Why is it so difficult to do this? The reason that it's too difficult is because the right-hand side is in English, and usually translation to English requires some sort of intelligence, and most of the compressors do not have intelligences. They usually come up with some algorithms, some intuitive ways of making the compression. Of course, we will do things mostly in that aspect, but this kind of a compression from 8 megabits to 13 bytes is seemingly possible. But this thing, the right-hand side, these 13 bytes with the phrase of blank picture or blank image. Blank images may be even a smaller thing, is essentially the information within a condition. It is a conditional information with the condition that the receiver or the decoder knows English.
I've got a question.
Yeah, yes, please.
Why it is 13 bytes?
Because there are 13 characters in this text. Blank
Thanks.
picture. Blank space picture contains 13 characters. And every character is represented using an ASCII code using 8 bits, which is 1 byte. So 13 characters is 13 bytes, isn't it? So the condition is decoder knows English. This is a huge condition. It's a very restrictive condition, actually, because knowing a human language at the side of the decoder is it's a strong requirement. Usually, the amount of conditions that we will have, both for the encoder and the decoder side, will be a settled algorithm. So the encoder knows the algorithm, and the decoder also knows the algorithm and uses the same algorithm to decode. Here, the algorithm is obviously the knowledge of this human language of English. And furthermore, the encoder needs to know something else. It must have a clever brain, a clever mind to see that, it's a blank image. When you look at that image, you see that it's blank. So let me say it in English, blank image, blank picture. And the decoder also knows English as well as knows things. It's like a human with some intelligence. And whenever he or she sees blank picture text on the screen, it says, it's a blank picture. What does a blank picture look like? It looks like this, okay? So that's how it decodes. This is too much, but it also shows an extreme case of information. So we are trying to reduce until the size of the information. We will see a few information measurement techniques, and we will use two of them. One of them, for measuring the information, the mutual information is the information in the computer world or in the digital sense, in the binary world, as a matter of fact. And that is the entropy due to Claude Shannon. So the Shannon entropy way of putting things is, first, there is a mutual entropy for a symbol. So we are talking with symbols. Okay, we must have some sort of a symbol alphabet for the representation. Otherwise, we cannot talk. A telecommunication requires talking. So we are talking with some symbols, with an alphabet. And those alphabet symbols have probabilities. A symbol, the ith symbol, has a probability of pi. Okay, and the size necessary for the transmission of this symbol due to Shannon is the logarithm of pi. The logarithm base is determined according to the digital structure that we are using, and typically for computers, of course, it's binary. Therefore, this logarithm is base 2. So this size gives you the size in terms of bits, binary digits, bits. That's why we are using logarithm base 2 for the representation of that symbol. Every time we encounter that symbol, we have to make that kind of a representation. And if we have several of these symbols, we have n different symbols, then this length, by the way, gives you a negative length because the um, probability is less than 1. It's something between 0 and 1. Every probability is between 0 and 1. And the logarithm of something like 1 over 2 in base 2 will be minus 1. So that length must be negated. So we put a minus sign, and we do it for all symbols. Okay, that will give you an average symbol length. Some symbols will be represented with larger lengths. Some of them will be represented with uh, longer lengths, longer bits. So we are trying to convert every symbol into bits, streams of bits, and some of these symbol bit sequences will be longer than the others. This is the Shannon way of looking at the concept of entropy and information. But the entropy, you may also know from other disciplines, for example, from physics or chemistry, that there is also something called entropy, which is more related to actually energy. And it's usually for continuously varying information. The information may be due to an alphabet, or it may be just a continuous function, let's say. For that continuous function, the energy that we will be talking about will then be in the form of an integral like this over time. We integrate the square of the function over time, and we come up with an energy term. This energy term, although it is a little bit unrelated to what we will be doing throughout this course, is essentially finding its way to our topics, to our concepts, in the form of a zero mean signal energy. So that will be the variance, which is the integral. By the way, the variance for discrete signals is also, it can also be defined. Similarly, for energy, for discrete signals, it's also defined in the form of a summation then, right? X square of n. The variance, however, is like x of t minus mu. The mean is removed, and then you take the square. Okay. Let me put dt. Actually, we need to put the probability density function as well. But anyway, let's do it like this. Now, these two are alternatively used in the concepts of compression and compressibility measurements. Sometimes we take a look at the variance of a signal, and sometimes we take a look at the entropy of a signal, whichever is more appropriate for us in terms of our measurements. Variance is also, therefore, some sort of a measurement of information because it corresponds to entropy, because it is energy. And since entropy in the discrete and in the continuous cases are similar, we can all use these things. By the way, in, of course, advanced physics, there are other types of energy or entropy definitions, like the entropy of a black hole and things like that. But we won't be dealing with those things. Although I strongly believe that, I'm pretty much sure that the information, the meaning must have some kind of similarities, and it must be measuring something. That is it's the name. Entropy is measuring the scatteredness of the data. If it is making a lot of fluctuations, then it is too much scattered, and its entropy is usually high. And similarly, if the variation is too much, the variance is also high. In fact, the terminology, the name variance comes from variation measure. Okay? Measures the variations. So they correspond to similar things, and they are all useful for measuring how much we can compress, how much variation it contains. But before these, uh, entropy stage, usually we do something else for better compression. We try to reduce the entropy of our source if it is not reduced already. For instance, suppose that you have a sine wave, an infinite sine wave actually. Now, as you see, in fact, the energy of this signal is infinity. It can be considered as a power signal because if you try to integrate the square of it throughout the time, it's diverging to infinity. So the amount of content that I have to transmit to the other side never finishes. Okay, it's infinite extent. However, if I take the Fourier transform of this signal, we all know that on the frequency axis, it makes only two impulses, right? Two impulses, just two values. And their values are conjugates of one another, by the way, independent from the phase of the sine wave. If it's a cosine, then the conjugate means they are the same. If it's a sine, they are the conjugates. But nevertheless, we have just two impulses. So two impulses can be, if they have different values, even if they have different values, require, I don't know, 32 bytes, 16 bytes for each value, 32 bytes, and one more, sorry, let's say 4 more bytes for this frequency, for the representation of this frequency. I'm trying to represent everything that can explain this Fourier transform, okay? I'm using 16 bytes for the left-hand impulse, 16 bytes for the right-hand impulse, and 4 bytes for the frequency because the other one is at minus of that frequency. So a total of 36 bytes. This is, by the way, infinity bytes. So what kind of a compression ratio? It's infinity. The compression ratio is infinity. What did I do? Did the information change? Well, actually, the information changed in terms of looking at the signal. Usually, if you look at the signal from one perspective, from the perspective of time axis, it looks quite complicated and quite long. Therefore, it requires a lot of energy or a lot of bytes for the transmission. It never ends. The transmission just never ends. However, if I take the Fourier transform, which means I'm looking at the signal from a frequency perspective, a Fourier perspective, and then suddenly it becomes just two impulses. Now, knowing this transformation or coming up with the idea of this transformation is the thing that we will try to learn. What could be a good way of looking at the signal from another perspective? And that is usually the first step that we apply. We have an input and we do a transform. An alternative to the transform is like we may do a prediction as well. We will talk about it. Sometimes prediction of the future sample and subtracting the prediction from the signal will reduce the variance and entropy significantly. So we do some entropy reducing techniques. We apply it as the first stage of the compression. Now I'm drawing the layout of the compression that we're talking about. Then, depending on whether we are doing a lossy compression or a lossless compression, we may apply a quantization. This quantization is usually applied in an optimal manner, and it is applied to the transform output or prediction output. And if you apply a quantization, as soon as you start applying a quantization, it means that you are doing essentially lossy compression. And then comes the lossless coder. This lossless coder is like the representation of the entropy, the eventual entropy at the quantizer output, and taking them as symbols with probabilities pi's. And now I am trying to reduce down to this much. Okay, and it is a lossless process. What are known techniques, for instance, for this lossless coder? One of them could be imagined as zip, right? In computers, we say zip or rar or something like that, right? They are all lossless encoders, and they are entropy coders that reduces the size. The effect of the reduction here is minimum. It's small, that is minimal uh, compression. I'm saying minimal, but it's because of the methodologies that we have. If you use the entropy definition of Claude Shannon, then usually the amount of compression that you obtain from the lossless coder is small. For example, if you have an executable or if you have a text file, when you zip it, it goes down to maybe half, sometimes as much as half, but usually much less than that. Like 1 megabytes will be compressed down to 800 kilobytes from this lossless coder part, from the end part. But when you have all of these things, the transform coder, the prediction, and if you apply it to even higher dimensional or longer multimedia signals, the size starts from audio signals, speech signals, for example. They are the shortest usually. And then images are usually larger in size of the information because they are two-dimensional. There is a horizontal dimension and a vertical one, and each of those horizontal directions could be considered as the one-dimensional signal, which may be audio, for example. So images are really larger than the audio. And if it becomes video, then it becomes even larger because we have frames of images for video, and the predictability, the transformability, efficiency, etc., they all improve as the size increases. So usually video is the most compressible data that we have in multimedia, and images are less compressible than videos, and audio is less compressible than images because they are smaller. If you go smaller and smaller, the compressibility reduces because the transform and prediction efficiency is usually reduced with reduced size. If the size increases, the transform and prediction efficiency becomes excellent. So this overall thing may really come up with some maximal compression. So this is the overall thing. But sometimes we may omit some parts of this. For instance, if you have a text or an executable file, of course, you just omit all these two parts and feed your data immediately from here and apply a lossless coding. Or if you are doing a biomedical signal compression, then this quantization is usually replaced by fine quantizer, almost no quantization, and you just apply a transform and then do some lossless coding so that the quantization, the loss is unnoticeable or there is no loss. because we know that biomedical images or biomedical signals in general are very critical things, and doctors don't want any loss of information over there. They want to see everything. They cannot tolerate a quantization loss. And sometimes we just do the quantization. We start with the quantization and then do the lossless coder without any transformation or anything. We feed the input immediately. But anyway, these three stages are the three fundamental stages. Also, I have to confess a little bit that although I write these three stages isolatedly, stage one and then stage two and then stage three, they may be interleaved. Okay, they may be fused to one another. Transform, for example, may include the quantization itself, or the prediction may include the quantization itself, and it usually does, by the way. So the quantizer part, if there is a quantizer part, it is usually incorporated throughout the transformation or the prediction part. So they are not very much separated and as individual as I draw here. And then, of course, we either transmit or store the encoded bit stream. These bits, if you're using some software programming, you must stack these bits, eventual encoder output bits, into 8-bit compartments, bins, and then say that it's 1 byte, and then you write 1 byte. And then 8 more bits, you write them, it's 1 byte. So byte by byte, you write it on the disk or you transmit, okay, stream. Um, the compression ratio for writing or for saving would correspond to a smaller file size, but if it's a streaming, it corresponds to bandwidth. How many megabits per second are you transmitting? Are you trying to transmit? So usually the transmission part is nowadays more critical for the necessity of compression, because if you try to compress an image, if you try to compress an audio, one may argue that nowadays the hard disk sizes are huge. Therefore, I don't need to compress a lot. It's okay. I have terabytes of hard disks. So let me just dump everything without compressing. Well, that's a choice, of course. Of course, you still want to reduce if it's a very large and high definition video, for instance, 8K video of 2 hours. Just calculate how many bytes you need for RGB, which is 3 bytes per pixel. 8K, how many megabytes of pixels for one frame you have to calculate, and then that would be for one frame only, and then you have, let's say, 30 frames per second, so multiply it by 30, that many megabytes, gigabytes per 1 second, and within 1 hour there are 3600 or 3600 seconds. So multiply it by 3600 for 1 hour and multiply further by 2 for 2 hours of video, and you will notice that your hard disk will fill with one movie or something if it is that much high resolution. But nevertheless, you can still say that I want to just store it without any compression, fine. But how are you going to stream it? The bandwidth for the wireless streaming, for the wireless communication to your telephone, it will be impossible for that kind of a high bit rate. We are trying to improve the bit rate through channel coding, combined channel and source coding using the 5th generation of uh, telephone communication standards, 5G, or wireless speeds are increasing. But actually, it's not really the speed that is increasing over there. It is also increasing slightly, but mostly it is the source compression, which reduces the bit rate and effectively expands at the decoder side. So you don't notice what's happening in between, and you feel that the bit rate is 10 megabits per second. Actually, it was 1 megabit per second physically, but 10 times compression was applied at the encoder side and at the decoder side, working simultaneously. So compression is still an issue. It's a necessity. So we do this, and the decoder just does the reverse in the reverse order, like first the lossless decoder, and then feeds it to the inverse quantization. It's sometimes difficult to explain what do we mean by quantization and then inverse quantization, because the idea of quantization in our minds is not settled yet. We will come to that topic later and we will discuss about it in more detail later. But actually, a quantizer is generating symbols. It's not generating values. For example, a round-off or a truncation strategy, we may think that it's applying a quantization. If it is between 0 and 1, it is quantized to 0. If it is between 1 and 2, it is quantized to 1 by truncation. You may think like that. So it's already making the values, and there is no inverse quantizer. Anything between 0 and 1 becomes 0. But it's not true. Actually, anything between 0 and 1 has now a representation at this stage. It's just a representation to indicate a value. There's a symbol, and it has symbol probabilities, and with that symbol probability, this lossless coder works. And it's not, the symbol is not 0, it may be something else. It may be 5. So the symbol is 5, and it corresponds to a value of 0. So where does it convert back to the value of 0? Coming back down to here and coming to here, this inverse quantizer takes the index value of 5 and it converts it to the value of 0, the output value. So everything between 0 and 1 as an input here is now represented by 0 at this inverse quantizer output. It is reevaluated here. And then, of course, whatever we do, it can be an inverse transformer or an inverse prediction. And generates the output. The input is X, the output is Y. After the encoder, X will be encoded into, let's say, C here, and C comes to here, and it will be decoded as Y. The bitwise representation of C must be, or should be, significantly lower than X. So the size of C is less than X. And it's also less than Y. By the way, the size of X and Y are the same. They are in the same dynamic variation range. But there's a difference between X and Y because of quantization, if there is a quantization, of course. And we want to minimize two things. Minimize the difference between X and Y in the average sense, which we will denote as mean squared error. So the expected value between X and Y must be minimized. Meanwhile, we also want to minimize the size of, let me put it like this, the size of C. So these two things must be done together, and they are usually contradictory to one another. If you are trying to minimize, let's say, the size of C, then the mean square error increases. Or if you want to minimize the mean square error, then the size of C increases, and they are inversely related to one another. The inverse is not, it doesn't have to be directly one over the other one. So one of them is not one over the other one, but it is proportional to one over the other one. And it is known as the famous rate distortion curve. The rate is analogous to C, and the distortion is actually mean squared error or something like that. So you cannot minimize both of them together. If you minimize one of them, the other one increases. If you minimize the other one increases. They are inversely proportional to one another, like this. And this is a fundamental outcome of the so-called information theory. So for the information theory, you must obey this rate distortion curve, and a compression methodology may give you this kind of a curve, whereas another compression method, let me draw it with red, for instance, may give you this. And as you see, the red one gives you smaller distortion at the same rate, right? This rate R, this is the distortion that one method provides, D1, distortion 1, and this is the other distortion that the other method provides, D2. So which compression method is better in this case? Clearly, the red one is a better compression. So we compare the lossy compressors, particularly, in terms of how they perform in the distortion sense at the same compression ratios. Or at the same distortion, what is the compression ratio? Similarly, at this distortion, for example, D, one of them gives a smaller rate, R1, than the other one, which is R2. Okay? So these are the fundamental issues that we will be talking about. And you have to be aware of how to calculate mean square error from data for practical purposes. For example, if you have a length, let's say n signal, and x of n comes in, and the output is y of n. How do you compute the mean square error? You just need to sum up x of n minus y of n and take the square of it for all n from 1 to capital N. Okay, and then divide everything by n. This is the mean squared error, for example. So this must be small, of course. We want y to be as close to x as possible. So x minus y is must be a small error, right, that we will be talking about. So this is the another fundamental issue that I want to mention before particularly diving into the compartments that I was talking about. What are the compartments? They are here. These boxes. We will be seeing a lot of methods, for instance, for this lossless coder. We will start with this lossless coding, and we will see some methods for this. And then we will continue with a part of prediction, I guess. I don't remember my notes, the ordering of my notes for the time being, but it doesn't really matter. After that, we will see a bit of quantization and how to optimize the quantizers. What do we mean by optimizing the quantizers? We have to decide on intervals to be represented with some value. So what is the best interval chopping? It doesn't have to be equal interval, which is called a uniform quantizer, but uniform quantizers are just very miserable quantizers in many cases. You can come up with much better quantizers than that. And then finally, we will be talking mostly about these transforms, because that is the place where most of the entropy reduction occurs. Have you noticed that in this example of the sine wave versus its Fourier transform, the information gain, the entropy gain was tremendous. Usually, it's the transform that contributes most to the entropy reduction. So it's important. The optimality of this transform is very important. And luckily, since this is a graduate course, in the undergraduate, we all know signals and systems. Therefore, we all know Fourier transform, which is a fantastic transform, by the way. But there are other transforms as well. And finally, if time permits, we will also be seeing some applications of this to, let's say, to some standards like JPEG. And for the video standards like MPEG and other video encoding systems, which has a unique and distinct way of making prediction. And these predictions are temporal predictions, frame by frame, a motion prediction particularly. If you're interested in, you may already start looking at how we really do motion prediction. Because as you see, I'm now streaming a video, and now look at the page, the screen that I'm sharing with the text. As you see, there is no motion. Therefore, for this video, the amount of residual information is having no motion or no extra entropy, and it is reduced a lot. But whenever I start moving, that makes a motion. And according to that kind of a motion, some motion vectors are being transmitted during the streaming. By the way, my camera setting is constantly streaming some motion vectors whenever I am doing some motion, but partially, as you see at the background, there is no motion. So the motions are also encoded according to their regions, region by region motion. That's very much specific to video coding. It's a huge topic, but we will just very briefly mention about if time permits. So these are the things that we will be doing. Now, before proceeding a little bit further about the further topics, maybe I may give an end within a few minutes. I want to mention about one critical aspect of wireless compression and wireless, or compression for wireless communication. Oops, sorry. And that is when this entity here is trying to communicate with this entity here. So this wants to transmit speech. So that guy has a phone and speaking or transmitting its video call, and it's arriving to the other side. Now, in terms of systematic or algorithmic way of making computations, if the computer of this one is very, very good, is very strong computer that may do a lot of fantastic video compression, motion estimations, etc., then it will be able to compress it in a very efficient manner, and the compression ratio will be very large, and therefore the data will arrive here, and the decoder computer for this one, for this receiver, could be a poor computer. Video encoding is very asymmetric to video decoding. Video encoding is very difficult because you have to measure how much motion is made, etc. It requires a lot of computations and lots of memory. It requires a very strong computer. But the decoder is not necessary for that. Even a telephone, a poor man's phone, can easily decode. All right. So it works if this computer is strong. and this computer is weak, it works. If this computer is strong also, it works, of course. It works even better. But even if this is weak, it works. Now, another interesting phenomenon happens like this. It's again from kind of information theory. If the computer of this one is poor, not strong, but it requires to reduce the data a lot because the bandwidth here is small. So I have to compress, but I cannot compress. So what do? I chop off data. Just eliminate a lot of data. I do a very, very bad compression, reducing the resolutions, reducing the frame rates, everything, etc. For the reduction of the data for compressing purposes. And then this part needs to reconstruct the data that is gone. And reconstruction is another aspect of signal processing, image, video processing, audio processing, etc., which requires a strong computer. If you have a strong computer and if you have a lot of memory and if you have time, then you can reconstruct it very well. Although, for example, the frame rate is 5 frames per second, you can interpolate the frame rate to make it 50 frames per second for smooth transition. Okay? If your computer is strong, you can even increase the resolution by making, uh, excuse me, this was a phone call and I will address. But I'm gonna finish within a few minutes. So the computer of the receiver needs to be strong if the computer of the transmitter is poor. Okay, but in wireless wireless telecommunication, there is one problem, and that problem is this: if this is poor and this is poor, how can they communicate? And unfortunately, in wireless communications, that is the case because this guy has a telephone, which is a poor computer, and this one also has a telephone, which is another poor computer. So we cannot push the power, the strength of this computational efficiency into either of these. They are both weak. So what we may do, a solution, is to put the so-called transcoder, which is an extremely powerful computer, and you can think of it as a base station. Okay, so in the base stations, if there are strong communication computer units, then it may take a very poorly generated input here, which cannot be reconstructed by this one, but it reconstructs it first. So the first part is, the left part is making reconstruction. And then after reconstruction, it must compress it again, but this time very efficiently, like a very strong computer that this should be doing. So at the second part, it makes the compression, efficient compression, so that this weak computer can easily decode it and transmit. And this one decodes it. So from here to here, everything is very efficient. It's very transparent, and you don't notice that there is actually a transcoder in between. But nevertheless, it is actually working like this. And in the recent generations of wireless communication, starting from 3G actually, these transcoders are actively working. And for 4G, we are needing and we are using even more efficient transcoders. And in 5G, probably there will be stronger transcoders in terms of base stations. And then, yeah, this is just a final remark that I would like to make, I wanted to make. So that's all I want to talk about for today, because starting from next week, we will be dealing with, again, measuring the entropy, because we will be doing the lossless coders. So this Shannon entropy will be important, and we will have to make an assessment about what 1 bit corresponds to, how much information does it contain. In fact, we will measure everything in terms of bit, so we will say that eventually 1 bit will have an information of 1 bit, and every additional bit will contribute twice the information. Okay, so with 3 bits, you have like 4 times the information of 1 bit, because for with 1 bit you can have 2 different values. With 3 bits you have 2 to the 3, which is 8 different values, and 8 different values is 4 times of 2 different values, right? So that measurement and how to construct something that is both efficient for bit generation at its output, efficient in terms of the generation of bits, as well as decodable. That is, the lossless decoder also exists, because sometimes we may just do some nasty things. In fact, in one of the news groups, in the ancient times before fire was invented, there used to be news groups on the internet, and it's even before internet. Okay, it cannot be even called internet, but yeah, nevertheless, let's say internet. There used to be news groups before email, and in those news groups, there was one very fantastic thing that I have encountered in the society of. There were societies in the news groups. In the society of compression, there was a post, and the post was like this. And immediately I saw the post. The guy says, "I found a method which can compress any input data to 1 bit." Okay, so everyone was furious. The answer posts were, "Hey, come on, you're kidding. What is it?" etc. And next day, he also posted a follow-up to this first post of, "I invented a method that can compress everything to 1 bit." The guy says, "I'm still working on the decoder side." Of course, there's no decoder for that. You cannot decode it. There are necessary conditions for the decodability. How much can you compress? And that is also related to the definition of the entropy, by the way. And not only that, it must be really obeying some further rules about decodability. So every code stream must be decodable. How can it be decodable? As a thought experiment, thought exercise, like a homework, you may say, but it's not a homework, it's just an exercise. Just study a little bit on the Morse code, okay? The ancient Morse codes of dots and dashes. And write something in Morse code and try to decode it using the Morse code alphabet that you have. And you will notice that it is not decodable because it's ambiguous. Dot dash dot dot dash may be decoded as something and something else too. So how do we decode it? It's not decodable. We don't want to obtain such non-decodable codes. Uh, but we are still using Morse codes, or people use Morse codes because they were using conditional entropy. They were assuming that the decoder is a human, so he will decode according to a reasonable word. There will be many words that can be decoded, but most of them will be meaningless words. But there will be one reasonable and meaningful decoding, and the human will automatically choose that meaningful one. But the computers will not be able to do that. So instead of that, we will try to obtain decodable lossless coders and efficient lossless coders too. But we will do all of these things starting next week at 9:30. So I want to stop now at this point. First, let me stop the recording.